I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about the algorithm alpha beta pruning. And first, we'll see what is the necessity of studying this alpha beta pruning algorithm. Studying the alpha beta pruning algorithm is essential because it optimizes decision making in game theory and artificial intelligence applications. This technique enhances the minimax algorithm by reducing the number of nodes evaluated, leading to faster and more efficient computations. Understanding alpha beta pruning is crucial for developing AI models that make strategic decisions in competitive environments like chess, tic tac toe, and other adversarial games. Moreover, efficiency improvement is a key reason for studying this algorithm. Without pruning, a game tree grows exponentially, making it computationally expensive to analyze all possible moves. Alpha beta pruning helps eliminate unnecessary evaluations, allowing AI to process deeper moves within the same time constraints. This makes the algorithm practical for real world applications where rapid decision making is required. Additionally, studying alpha beta pruning strengthens problem solving skills and provides insight into the optimization techniques in computer science. It teaches students and researchers how to improve performance in AI driven applications such as robotics, strategic planning, and automated decision making systems, etc. By mastering this concept, we can develop smarter, more efficient algorithms capable of handling complex decision trees. Okay, thus, alpha beta pruning is a fundamental concept in AI and game theory, and its study is necessary for anyone working in the fields related to AI, machine learning, and algorithm design. We'll see the basic steps involved in alpha beta pruning algorithm. First, we'll see the introduction to alpha beta pruning. This alpha beta pruning is used in the optimization in decision making. How it is being used? Alpha beta pruning is powerful technique used to enhance the efficiency of minimax algorithm, which is widely applied in decision making scenarios, especially in game AI. By strategically pruning branches that do not contribute to the optimal decision, it reduces computational overhead, allowing faster and more efficient decision making. This ensures that only relevant moves are analyzed, making the process more scalable and effective in complex game scenarios. Next, eliminating unnecessary computations. It will be doing it. One of the primary benefits of alpha beta pruning is is its ability to eliminate branches that do not affect the final decision. In a game theory, many branches contain suboptimal moves that do not need evaluation. By cutting off these unnecessary calculations, the algorithm significantly reduces the number of nodes it processes, leading to faster computations while maintaining the same final decision quality. Next, managing alpha beta values. The efficiency of alpha beta pruning relies on maintaining two key values. What are they? Alpha, that is, this symbol is given by alpha, and beta, right? Alpha represents the best option available to the maximizer, while beta represents the best optimizer available, that is minimizer, available to the minimizer. As the algorithm explores the game tree, it updates the values dynamically, ensuring that branches violating the alpha is greater than or equal to beta condition are pruned. This selective evaluation helps to avoid the redundant computations and focuses on the most promising path. Next, how it is being used in the real world applications. Alpha beta pruning is extensively used in AI for strategic game like chess, where the number of possible moves can be overwhelming. By pruning irrelevant part of the game tree, the algorithm enables AI system to analyze more profound strategies efficiently. This technique is not only speeds up decision making but also enhances AI performances, making it a crucial tool in game theory and competitive AI systems. Now we'll see one example problem for this alpha beta pruning. This is the example problem, the tree problem. We have taken it over here. And the first step involved here, this row represents the maximizing value. This is minimum and this is maximum. This last row values are calling it as the terminal node values, that is leaf node values. The first step involved in alpha beta pruning is initialization of alpha and beta. The algorithms, where the algorithm starts at the root node. Here, the root node initialize that this root node A, this value contains the maximum with the initial value is what? Alpha is equal to minus infinity and beta is equal to plus infinity. Alpha is equal to minus infinity, beta is equal to plus infinity. These values represents the worst possible scores of the scores that maximizer and minimizer can achieve at this point. The values are passed to the node B. Here, these two values are being passed to the node B, that is the minimal. This is the minimal value, which also starts with here this value directly transmitted to here, alpha is equal to minus infinity and beta is equal to plus infinity over here. The same values are forwarded to the node D also. Here the same values, alpha is equal to minus infinity, beta is equal to plus infinity. And the next step is, so what I have told you here, this value will be transformed here and this value will be passed over here. So alpha is equal to minus infinity and beta is equal to plus infinity. So what is the next step to be followed in this case is the backtracking. Node B, and first evaluating the next step is evaluating the node D. And since node D is this node is a maximum or min node. Since the node is a max node, it evaluates its two child nodes, here 2 and 3, which have their two child nodes have the values this 2 and 3. The maximizer selects the highest value from its children. So the maximizes maximum of 2 comma 3 was what? The value is 3 will be selected. Now the value of alpha at D is updated to, here alpha value is minus infinity. Which one is maximum? Minus infinity or 3? So now the value of alpha at node D is, I'll be writing in different color. Now the alpha value is updated to, here it will select 3. So now the alpha value at D is updated to 3. The D returns this value to its parent node. It will be returning to this parent node B. Okay. Next, backtracking node. Next, the third step is backtracking node B. At node B, what is the value will be selected? B. Here now the value alpha is, in the previous step we got 3 and beta is equal to plus infinity, right? And it is now the minimizer turns to update beta. Now which one we have to update? The beta value should be updated. Since beta represents the best minimum values seen so far, it is updated as a minimum of plus infinity comma 3, plus infinity comma 3. Which one will be selected? Plus infinity minimum of as I have written, minimum of plus infinity 3 means the value is equal to 3, right? Now the node B has alpha is equal to minus infinity. In this case, alpha is equal to minus infinity and beta value is what? Now the beta value is equal to plus 3, and these values are passed towards next child node E. So this value, no, alpha is equal to, here this value will be passed, plus infinity, beta is equal to 3. It will be passed to the next child node E. So here it will be selecting maximum, it will be selecting node C. Evaluating, we have to evaluate the node D. Next, the step is here now the alpha values in the previous case. Alpha is equal to minus infinity and beta is equal to 3. Now we are going to evaluate the node E. At node E, that is the maximum, E of max. What we have to write? E of max. Here I have written no? The E of max. The maximizer starts evaluating its children. The first child has a value of 5. The first child has a value of 5, and alpha is updated to maximum of alpha comma 5, that is alpha minus infinity comma 5. Which one will be selected? Maximum of minus infinity comma 5 will be is equal to 5, because this value is less than that of 5. Now since alpha of here now alpha of what? Alpha of, in this case, alpha is 5, that is alpha of 5 is greater than what? Greater than beta of 3. Beta of 3 at node B. Here in this case, node B, the pruning condition alpha is pruning. What is the pruning condition? Alpha should be greater than or equal to B is met, meaning the right child of E value, the right child of E value is being pruned. This value is going to be pruned. So the pruned value we have to mark like this. It should be ignored. Thus pruning occurs and node E returns to node B again. So pruning had happened here. So it will be returning to the node B. Next step is evaluating node F. Next we have to go to backtracking A. Next, backtracking A. This pruning, the backtracking node A. So this value will be backtracked to node A. After evaluating both the children, node B minimum selects minimum of 3 comma 5 equal to 3 and returns what? 3 to node A, and here 3 will be returned over here, and now the A of max updates to alpha to max of alpha, that is max of that is infinity comma 3, max of max is equal to 3. See here, the max of 3. What is the value? 3. This value is now passed to the right child. What is the right child? Right child is C, minimum, along with the beta. Here, alpha value is equal to, alpha is 3 and beta is equal to minus infinity. Now, we have to check. Next node, evaluating after backtracking node A, evaluating the node F here. So now alpha we got the value at node C of minimum, alpha and beta value, or here alpha is equal to 3, and what is the beta value? Beta is equal to plus infinity. The first child of C is node F. Here, yeah, what we have to find out? F max. F max we have to, so this value we have to find out, which evaluates its two child values 0 and 1. So what is the maximum value? Since f is a max node, it selects the highest value. So max of 0 comma 1. What the value will be selected? 1 will be selected. The node value of f is, now what is the node value of f? F is 1, and this value is returned to the 1. 1 should be returned to where? Returned to node C. Next. So in this case, no return C. So the 1 should be returned to C. Now we have to prune at C. Now the node C minimum. Now the node C minimum beta is updated what? Beta of alpha comma 1. What is the minimum value? 1 will be selected. Since alpha is alpha of 3, since alpha of the here, see here, alpha of 3 is, beta is greater than or equal to 1. That is alpha of, what we have to write? Alpha of 3 is greater than or equal to beta of 1. Beta of 1 at node C, pruning occurs. This means the second child node G max and its subtree or exactly here this alpha value is greater than beta of 1. This node and everything will be pruned. So node C pruning occurs. This means the second child node of G max and its subtree are ignored as they will not influence the final result. Thus C returns 1 to node A. Here 1 to node A without evaluating node G. This has been pruned without evaluating this one. It will be returned to the A. So now the final computation at the final step, node A max. What is the A max value? Here, A max of value. A of A max of what we have to write here, maximum of 3 comma 1. Which value will be selected? 3, maximum of 3. This means the optimal value for the maximizer is 3. The algorithm successfully avoided unnecessary calculations through alpha beta pruning, making the process more efficient by reducing number of evaluated nodes. So what I have written, maximum of 3. So the optimal value 3 is being selected. So this completes the alpha beta pruning process where pruning helped us skip unnecessary calculation while still determining the correct optimal value. And what are all the key takeaways from this alpha beta pruning? That means the impact. We can call it as impact of alpha beta pruning. Alpha beta pruning plays a crucial role in reducing unnecessary computations by eliminating branches that do not influence the final decisions. In this case, so in this example, what was pruned? Node G was ignored because the condition alpha is greater than or equal to beta was met at node C. This saved the algorithm from evaluating two extra terminal points. What are all the extra terminal points? This 7 and 5. Two extra terminal points, 7 and 5, and reducing the overall computation time. Next, by avoiding these unnecessary calculations, the algorithm remained coefficient while still arriving at the correct decisions. Additionally, optimal decision making was achieved without traversing the entire tree. The maximizer at node A was able to determine its best possible move by only evaluating necessary nodes. Since the algorithm pruned unneeded branches, it eliminated redundant work while maintaining accuracy. Overall, alpha beta pruning significantly improved efficiency by reducing the number of nodes evaluated, allowing for faster decision making. This makes this especially useful in complex decision trees such as those used in game playing AI, where evaluating every possible move is computationally expensive. The technique ensures that only relevant branches are explored, optimizing performances without compromising the connections. So this is what we are doing it in the alpha beta pruning. So only thing what we have to remember is what is the first alpha and beta value, what it has to be moved into the B. Next, what is the thing to be pruned? Once if it reaches alpha is greater than beta, the remaining node should be pruned. So very simple steps only followed in this alpha beta pruning techniques. Hope everyone enjoyed this lecture about alpha beta pruning. The remaining things we'll discuss in the next lecture. Thank you.